So appreciate the opportunity to come and give a keynote at this event. This is my first Moabcon. Looks nicer outside than inside. And so it's great to line this up with the last week of skiing, but there's a problem with solving in the conference room. The skiing's out there. So I'm going to try and sneak a little bit in here at the end of the week here. So my role at Intel is I'm Director of Technical Computing Software. I'm also Chief Technologist for Technical Computing Software in our Software and Services group. So I work with all the folks at Intel who deliver software and software-related capabilities into the technical computing market, which includes HPC workstation, our new Intel Xeon Phi mini-core line, and also our new activities around high-performance fabrics with our acquisition of InfiniBand technologies from TrueScale. Today I want to talk to you a little bit about the challenges of getting to exascale. I guess I'm blocking my slides. There's no great place to stand, maybe here. The challenges of getting to exascale. And we'll focus in on the processor, which is one of the main things Intel does, but we're not going to talk just about the processor. There are many, many challenges in getting to exascale. I want to motivate that with all those challenges, you want to create the most productive path possible. And that's what Intel's trying to do. So I don't think I need to tell anyone in this audience about all the exciting science that's still unsolved, exciting engineering that's unsolved, climate forecasting, climate research, weather forecasting, solving some of the toughest diseases, getting cures for cancer, genomics, medical imaging. But there's many problems that motivate exascale, and you can go to almost any HPC conference and get a great talk about why we need exascale and why it's going to be very hard to get by 2020. So as we approach exascale, is everything okay? Sorry, thought maybe I was being an interruption. As we approach exascale, there's a lot of opinions about what it's going to take to get there. And one thing that Intel is doing is looking at what we believe are some of the myths, what some believe and what we believe. Though some will tell you that there's no way to get to exascale with current technologies or the current path we're on, that you have to do something radically different in the architecture. We think there's a need for tremendous innovation, but that's not the same thing as radical changes in the architecture. We don't want you to have to throw away all your code. We don't want you to have to forget everything you did over the last 20 or 30 years to get this far, to get to petascale. So some believe that it's completely new, that it's a complete revolution. We believe it's an evolution plus some revolutionary ideas. But we also believe that something is going to change. The ability to simply take off-the-shelf components, integrate them, and create world-class systems is going to get harder and harder. We need true co-design between the system software, the application software, and the actual hardware. And that's the multiple fronts that Intel is working with the industry to attack this problem. So fundamental to all this is, our processor is going to keep getting faster or not. There's many people who said Moore's Law couldn't continue, and I'm glad to announce that, I remind you that Moore's Law is alive and well. But one thing you'll notice is that every time Intel and the industry has done a shrink, going from 90 nanometer line widths in 2003 down to where we are today with 22 nanometer, we haven't just shrunk the line widths. There have been other innovations that have come along, strained silicon, high-K gates, and now Intel's the first to introduce the tri-gate transistor, the 3D transistor. Each of these innovations helps us stay on the curve and keep things going. So the other claim that's been made, and we don't believe, and we're proud to have proved it in our labs, and Troy's going to tell you about it in a minute, how they proved it in their environment, is that you don't have to go to a radically new architecture to achieve breakthrough performance and power efficiency simultaneously. You can do it by taking the ideas that we've applied so far, applying Moore's Law, applying more parallelism. You can get there. And this slide is just a comparison. You can look at it, says, you know, even though there are claims out there that you have to do this with a GPU, Intel demonstrated you can do it with a mini-core Intel chip. We have leading power performance in the industry with our Intel Xeon Phi, and that's the first product. Another claim that's out there is that caches are dead. Caches aren't going to help you. We've got to manually manage the locality of all memory accesses. Intel does believe that you have to be extremely careful with your accesses of memory, the way you deal with the memory subsystem. And it's going to become increasingly important as you move to exascale because the energy is lost in moving data. So we're looking at the interconnects, we're looking at the memory architectures, but caches are very powerful and they're going to help us along the way. And what this chart shows you is that if you take the baseline of 1, you know, what is the bandwidth and what is the what is the bandwidth per watt that I can achieve out of a standard memory subsystem, and compare it to the L1 and L2 caches, you see what everybody knows is that you can get 15x improvement in bandwidth by going to a cache. That doesn't surprise many people, but many don't know that it's over a 40x improvement of bandwidth per watt. So caches have a role to play. We believe some of the architectures that are out there that don't use caches, you're going to see them getting adopted. So this technology is not going away. I mentioned that we have some claims, but Troy and team have done some amazing things in terms of demonstrating at a system level the most power efficient system in the world. And I think, Troy, you're going to talk about that in your talk, so I'm not going to say more about it, except that we're delighted to have partnered with Oak Ridge and UT and NICS on this effort. And we're delighted with the result. So the main challenges in achieving exascale are going to be around managing the power and managing the reliability. I think anybody can do the arithmetic and say, okay, I know what the path is of the processor, I know what the path is of the fabric, I know what the path is of the memory, and do the arithmetic and figure out how big a system it needs to be for exascale. And it's something you could build today. The problem is it would take anywhere from 60, 70, or maybe even 100 megawatts to run that machine. So how many nuclear power plants are we willing to build to power a computer to solve science? And how much climate impact are we willing to have in order to study climate impact? It gets kind of ironic. So the challenge in the industry is how do you do that in a more reasonable power envelope? And the one that people have been focusing on is more around 20 megawatts. And that's going to require the innovations from Moore's Law, but it's going to require a lot more innovations. Many, many fronts. We're going to have to improve the memory power performance, the processor power performance, the interconnect, and the data center itself. And I've got some of the factors and some of the approaches that we want to take, and we're looking at all of these now. But this is not going to be solved just with CPUs or just by building better data centers. We need innovations and breakthroughs across every front. And the innovations and breakthroughs that we achieve are going to have an impact on the way you program the system. So again, let's keep as much as we can. Let's not throw away things unnecessarily. That's Intel's philosophy. The other challenge I mentioned is reliability and scale. If you look at Intel Xeon processors, we have wonderful reliability. Very, very long time mean time to failure, mean time to interrupt. But when you put hundreds of thousands of those together, your mean time to interrupt starts to get shorter and shorter. And in fact, if you do the math, if you take the system scale out to what it needs to be, growing and growing the system, you have to look at the top 500 and see that it's actually growing at twice Moore's Law. So you're getting some of your performance from improved system components, but you're getting an equal amount of performance coming from the larger and larger scale systems. So you're getting up to hundreds of thousands, even millions of nodes. And when you do that, I'm talking about CPU, but the same story with memory. The mean time to failure is dropping precipitously. Meanwhile, the time to actually do a checkpoint is growing. And there's a point, it's not so far out in the future, when it will take equal time to checkpoint your system as it does to run a time step. And that means you can never do better than 50% efficiency. I don't think any of us want to build one of the world's most capable systems and say to the National Science Foundation or the DOE or whoever your funding agency is, but I can only get half of its potential. I'm spending the other half time writing data. So we've got some interesting challenges to face in terms of both making systems more reliable, but also dealing with failures on the fly, dealing with checkpoints on the fly, and doing them asynchronously. And again, that's an area of active research. So now I want to narrow and come and just talk about CPUs. We can talk about the other aspects another time. I'd be happy to talk with you offline, but I need to pick one thing. I'd like to talk about the Xeon Phi processor and how it fits into this story. So Intel's got two main product lines for high-performance computing. The first is the Intel Xeon processor. This is your general-purpose workhorse. You'll find it at the heart of the biggest systems in the world. You'll find it at the heart of the most productive systems in the world. The systems where you find Xeon Phi, you usually find them attached to an Intel Xeon processor. I don't want to give any illusions that Intel Xeon Phi is for everyone. Intel Xeon Phi is for a very specific audience, a very specific set of applications. We're going to talk about that. But I don't want you to forget that Xeon is a great processor for general purpose needs. Xeon Phi is different. It's a specialized product that addresses a specialized subset of the workloads, ones that are highly parallel or highly parallel phases. And what I'm going to spend the rest of the time on is talking about how you can figure out which one your code fits into, how you can program each of them productively, and how you can get on the path to taking advantage of the extra power of Xeon Phi while making progress on Intel Xeon today. And that's the heart of Intel's productivity story. So a quick plug for our Xeon processor. The latest, our Sandy Bridge generation, Xeon E5. We were able to improve performance 73% in some cases by bringing applications forward. Many industry benchmarks doubled in performance, which we were very proud of that generation to generation, because that's more than you get from Moore's Law. We also were able to extend our instruction set to put more parallelism through the advanced vector instructions and extension to AVX. And finally, we improved and integrated our I/O with PCI Express integration. That's allowed us to really reduce some of the overheads that exist in dealing with high-performance networks. And I think you're all aware that InfiniBand has dropped down to under a microsecond end-to-end latency from applications. Every little bit of overhead in the software, the hardware, and the I/O needs to be addressed. And this is one of the first things we're doing to help with that. Switching over to Intel Xeon Phi, it's a groundbreaking architecture. It's very different in many ways. It's a different design center fundamentally. There really isn't any other huge difference between it and a traditional multi-core chip. It's just a mini-core chip. We decided to put a lot more cores. Each of them is less powerful, but in aggregate they're more powerful. And this is the trade-off that the industry, everyone in the industry knows how to make and has in front of them. We can't do it for the whole Xeon line because there are too many codes that aren't parallel enough. But there are enough codes that are parallel enough to actually justify creating this product, and that's why we've done it. 61 I/8 cores, up to 244 hardware threads. A lot of memory on the card, 8 gigabytes, so that you can put real codes on the thing. We've got 512 wide registers. This is a doubling again over the AVX. The card runs Linux. It shows up as a node on your network with an IP address. That opens up some possibilities that we'll talk about. And it runs standard programming languages and uses standard tools, again, making it more productive. So with this, we've been able to break the 1 teraflop barrier for double precision peak performance. We've doubled the memory bandwidth relative to a platform, not relative to a Xeon socket, to a platform. And in many cases, we've been able to achieve 4x performance per watt advantage. So I want to show you where it fits. And I really want you to focus on this plateau of blue here, which is way under 1. Those are all the places Xeon Phi is going to be slower than Xeon. Most of the world. But that's because most of the world is not highly parallel. Most of the world is not highly vectorized. Okay? But if you can parallelize your code, get in the plus 90%, 95%, everybody can do Amdahl's law and figure out what's needed for a system of this scale. If you can vectorize your code and take advantage of the instruction level parallelism that exists with those 512-bit wide registers, then you push your code out in this corner, and this starts to tap into some really significant performance opportunities. But the key is knowing where your application fits. The other thing to think about is, if your whole application has these characteristics, awesome. We can give you a really productive story there. If your application only has sections where it's highly parallel, then you're going to have to work a little bit harder, but we still think we can make it easier than the offload languages that our competition offers. So I want to show you a few examples of performance, to make real the claims that if you trade peak performance with more parallelism for generality, with something like a general purpose processor like Xeon, that you can get these results. So, I apologize, it looks like the layout changed a little bit on display, but the numbers are hidden. But what you see here is across the board, a 2x to 3x opportunity on micro benchmarks relative to Xeon. And we don't mean a single Xeon socket, we mean 1 Xeon Phi coprocessor, and these are ratios relative to 2 state-of-the-art Sandy Bridge Xeon E5 sockets. So it's a whole Xeon platform, and then the 1 Xeon Phi card. So about 2.9x on math, SGEM and DGEM, your matrix multiply. Same with HP LIMPAC, over 2x, almost 3x, and 2x the stream performance at a platform level, again. So it's a lot of raw performance if you have highly parallel codes, and these are highly parallel. So how does that translate into performance? And And it may be disappointing for me to say a Xeon Phi is going to give you 2 or 3x gain relative to a Xeon platform. So I'm sure how many people have heard claims of 100x from accelerators. Anyone? Nobody? People just don't like to raise their hands. I understand it's really early, it's tiring, and we're out late. The reality is the way you can achieve 100x, 200x, 300x performance gain with an accelerator or any highly parallel processor is to make sure you start with a dog-slope comparison. So if you'd like to see that Xeon Phi is 340x faster, I have the case study for you here. We start with a non-parallel, non-vectorized, low-optimized, single-threaded math thing. In this case, it's just a simple matrix multiply math thing. Matrix multiply runs in 67 seconds. And then you insert some directives, and you throw out some optimizations for parallelization, and you get the thing to run in 0.2 seconds on Phi, and you get a 340x speed up. What a lot of people don't do when they quote these numbers is go and take that code back to a Xeon and see what that processor could have done with that same highly vectorized, highly parallel code. In this case, the Xeon runs at 0.46 seconds. So we got more about a 2.3x, which is consistent with what you saw in terms of peak performance. And it's pretty logical to think if the platform peak performance difference is only a factor of 2 or 3, then if I'm seeing 100x, it's probably not that the new thing is great, it's that my code really was awful before on the old platform. And that's what we've seen over and over in our engagements with both labs and with commercial entities across oil and gas, financial services, climate forecasting, Monte Carlo applications, and QCD, is that when people actually put their mind to it and write good code, they are getting real gains, but they're not 100x. So I want to give you one example that's relatively new and we're actually very excited about. How many people are familiar with the results that came out of WRF 3, maybe 4 years ago on an accelerator where one of the functions was sped up about a factor of 5? Do you guys remember that work? Okay, not familiar with it. John Michalakis, I hope I'm pronouncing his name correctly, did that work?
You are.
You are?
Yeah.
Oh, I'm getting it right.
That's one desk over from me.
Awesome. So he did some really neat work and wrote a paper that talked about the potential of highly parallel systems. In this case, he was looking at an accelerator. And I think the number he got was about 5x gain on this key function. But when he took into account the time to transfer data back and forth, he took into account the fact that there was just one function in a larger, much complex application, there really wasn't any application level gain to speak of. And the work to do it was pretty significant. An Intel team working in conjunction with NREL weather channel companies, have actually been working with WRF using it in a native mode where we just treated the Intel Xeon Phi as a computer, not as an offload engine, but as a computer. So there were no data transfers. Put the application on there and they just worked through the most parallel parts and got them tuned up and are now able to see a 45% improvement over the Xeon platform at the application level, running a real workload. This is on a 4-node cluster, so there was actual communication between the Xeon Phis, and it's apples to apples. A 4-node 2-socket Xeon cluster compared to a 4-node, the identical cluster with Xeon Phi cards added. And this is a pretty exciting application level result. A few more examples real quickly. Sandia National Labs with their mini-FE finite element code. Again, in this native mode, 2x performance. A couple examples from the seismic industry, one from Accelware, one from a Chinese oil company, 2x. Internally, our Intel labs have done some really cool work with ray tracing. This is already a ray tracer that's much faster than what you'll see out in the industry. It's a groundbreaking ray tracer, but it's 2x faster roughly on Xeon Phi versus the comparable 2-socket platform. And through QCD and in the finance industry with some Black-Scholes and Monte Carlo. So we're seeing real examples at the application level of people achieving great performance. And this is with fully parallel applications, not offload. They're living in that corner of the chart I showed you. So how do you get there? What I've claimed is we actually can advance the industry by just picking a different design point. More cores, each core is less powerful, but if you can aggregate them effectively, you can get more overall performance. Right? So it's just a design trade-off. And we've created 2 products. Xeon, which will be our baseline, and the mini-core product line, Xeon Phi, with wider vectors, with more parallelism, and so on. But the thing we've done is we've made sure that all of the programming models, all the tools that we developed for Xeon work the same, work equally well on Xeon Phi. What that means is you can take your code and recompile it and put it on Xeon Phi and do some experiments and find out if it's for you, find out if it works. Use performance analysis tools and figure out where you are and where you aren't getting performance with differential profiles, for example. So it gives you a really quick start, a quick introduction to the architecture. And if Xeon Phi is not right for your code, you'll find out quickly and you go back to work. And we think that's part of the productivity story as well, is not wasting your time on something that's going to be a fruitless endeavor. So this image tries to illustrate that point. What I've graphed here is the number of threads I'm using across the x-axis and the performance I'm able to achieve in an absolute sense in the vertical axis. And two things to take away from the slide. First one is, if you really can't use all those threads, and remember, generating threads is not the goal in HPC. It's harnessing parallelism because you have to. We don't like parallelism, at least I don't. Right? We do it because we have to. It's the way we get access to performance. So it's not just a matter of generating more threads, it's actually about maintaining parallel efficiency as you work your way to the right. And how many people have codes that have parallel efficiency on a per node basis that could get to 240 threads? Probably some of you, but not a lot. Right? So that's the future for us. But there are some people, I just showed you some examples of people who have that. And I think now that we've got hardware we can run on, more and more people pushing their codes in that direction. So it's a slow start. In fact, you've got to get out to maybe 4x the number of threads, or 5x the number of threads on a Xeon Phi before you match the performance potential of the Xeon platform. Right? So unless your code is ready to make that ride all the way to the right, you're better off sticking with Xeon. So you need more threads to achieve the same performance, and the same thread count, if you read these vertically, can actually achieve less performance than Phi. So again, this is a platform for highly parallel application. Again, I apologize, the word applications disappeared here. Something with the presentation, the formatting changed. Okay. So the keys, how do you unlock the performance potential of an Intel Xeon Phi processor? The first thing is make sure your code scales. High parallel efficiencies, all the way up to very high thread counts or process counts. I'm using thread in a general sense here. Make good use of vectorization. That's where the power is in these chips. 512-bit wide registers that can do math operations in parallel within the instructions, within the registers. Pay attention to your memory usage. If your application is memory bound, you're still going to feel that. There is a lot more memory bandwidth on Xeon Phi, but not infinitely more. So pay attention to how you manage the compute resources, how you manage the memory subsystem, and you can start to tap into the power of this chip. And then finally, thread level or MPI level parallelism. We'll talk a little bit more about the trade-offs there and how they can be mixed. But that has to be there for you. If all those are true, this may be a suitable architecture for you. If not, Intel Xeon is there for you. Keep you moving forward. So Intel is very big on standards, and we've embraced all the key standards in high-performance computing. And we're looking carefully at emerging standards. But if you look across the range of things, ways you can extract parallelism, the reality is there's no one-size-fits-all. If you're doing something in C++, you can take advantage of highly parallel template libraries or something like Intel threading building blocks. If you've got OpenMP code that needs to port across many platforms, we support that. If you've got MPI code, most of us do, that needs to run very well. You have calls to solvers and to BLAS3 and FFTs. We have Intel math kernel libraries. So we provide this range of ways to extract parallelism. OpenCL is up there, which is an emerging standard and starting to get established. We support all these as well as we can. Try to put world-leading implementations out there. But the key is the same set of things we recommend for Xeon are going to run on Xeon Phi. You don't have to introduce a new model. So just this visually summarizes what I've been saying. We believe you should be able to take the same source code base and port it almost seamlessly and run it on a Xeon, a multi-core chip, run it on a mini-core chip, run it on a cluster of all multi-core or a mix of multi-core and mini-core. Maximum code reuse. Now we're not saying that you won't have some tuning to do. We're not saying that you won't have to change your code to extract all that parallelism and get out in that corner. That's real work, and no tools and no architecture can do that for you. But we can make it as easy as possible by not forcing you to fork your code base, not forcing you to send a graduate student or a postdoc off to investigate for a year what can be done with an architecture, get some results, and then find that the code has moved forward, the science has moved forward, and there's no way to integrate that back in. I've seen that happen too many times, where good work, innovative work, takes place, but it can't get integrated back in because the science moves forward in a team environment. Our goal is to allow you to do those explorations and move the whole code base forward to get the results from your work. So the products that we offer, and this is not a product pitch, but I want to at least show them, the products that we offer to implement all these parallel models, support them with runtimes, support them with high-performance libraries, support them with analysis tools, is our Studio product line. If you're working within a single node, and I don't think many people in HPC are, but many people in technical computing are, just not HPC, Parallel Studio XE has what you need. It's got C and C++ and Fortran compilers, OpenMP, math kernel libraries, Silk Plus, which if you haven't played with that, is a really great way to get into Parallelism easily, and Intel's working to drive that into GCC. Open up our libraries so that we can implement it all over the place so that you don't have to worry about getting stuck with some Intel-only solution. And then our analysis tools, the B-Tune amplifier, and our advisor, which helps you actually get your parallel application correct. When you move to a cluster, we take all of that, and then we add an Intel MPI library, which is an MPICH2-based library, multi-fabric library, very high performance, very portable, and we augment that with the Intel Trace Analyzer and Collector, which allows you to get insight into your MPI applications. I just wanted to show you this quote from Robert Harrison. That was at NICS at the time. He's moved on now, but when he got his hands on his Intel Xeon Phi, started looking at it, and came back to us and said, we were able to port, in a matter of days, millions of lines of code and get them up and running and confirm the results were right. That was an amazing quick start. He said, not only did it get us started faster, this is code that doesn't run on GPUs and never will. Because the idea of trying to port all that code to a GPU so then you can start looking at the performance opportunities was daunting. But with Xeon Phi, they were able to port all the code and then look for the opportunities using standard tools. It was a huge productivity boost. So I want to spend the last time here really talking about the programming models we support. And I'm also going to talk about the operational models, because I think a lot of folks in the audience have to manage clusters, right? And you want to understand how are users going to program these, and how do I need to present these Xeon Phi Coprocessors, the Intel Xeon processors, this more complex environment to my users, and manage it. So let's start from a programmer's perspective. The world up until now has been what I call multi-core centric, and that's this leftmost column where you have some main program, or Fortran or C, you do some work, I'm calling it foo, you do some message passing with MPI, but you're talking over a network to a bunch of other CPUs, 1 or 2 or 4 robots. That's the multi-core centric model. What I described for you with these performance examples is people who've been able to take their code and deal with the Intel Xeon Phi as if it were a standalone computer. Over there, that's this many-core hosted model. Our chips run Linux. You can log into them. You can compile and run codes without changing them in most cases. And that's the many-core centric model. So if you're lucky enough to have a code that's highly parallel, has enough parallelism, incredibly productive path to work on the right. If you're one of the unlucky folks who has a code that's it's serial, but it's got some highly parallel phases, and highly parallel could just mean that you have to do some I/O up front, and then you go into a solver, and it goes out. You're going to have to deal with some of this stuff in the middle. And you'll have to think about whether you want to run your main code, and then when the time comes to do this compute-intensive piece, do an offload, right? Send it over to the Xeon Phi, get that calculation done faster. You can do it asynchronously. You can overlap communication and computation. I'm not going to get into that today. But all the standard tricks for extracting performance in a distributed system apply here. And we provide mechanisms for that, many choices. You can do it with MPI. You can do it with an offload language, which is feeding into the next OpenMP 4.0 spec, which is under review now. And we're hoping that it will come out with these capabilities soon. You can go symmetric, which is just load up MPI processes, recognizing the different characteristics of the Xeon processors and the Xeon Phi, and divide up the work and maybe even put different types of work, a heterogeneous calculation on that system. All of your communications, all your capabilities are homogeneous, but you change the workload to map to the characteristics of the machine. That's a symmetric mode. And we've had some folks who've had real good luck with that. And there's even another model, which I don't show here, which is a reverse offload notion, which is my code is highly parallel, it just happens to have some serial phases. Maybe checkpoint, I couldn't parallelize. So why not compile that over here, and then have a service process sitting on Xeon who does that fast I/O for you. There was a lot of success with that model, actually, at the Roadrunner system, which was recently retired. And you can go out and look up a paper by Scott Pakin, where he talks about the productivity advantages of actually figuring out where most of your code is, and porting it directly over here, and then just dealing with the serial phases from that. That's called reverse offload. I don't show that here because we don't have specific tool support for that, but the system supports it, MPI supports it, and you can use any standard model you want to achieve it. So why the range of models instead of one? Because there's so many differences in codes, differences in workloads. The folks who have highly parallel workloads don't want to be constrained by having to work with an offload language, ship data back and forth. The folks who don't have highly parallel code can't take advantage of that very productive mode on the right, but they want to be able to still take advantage of this architecture. So we offer the different options to fit your code. And for the most part, I think folks can understand where their codes fit. We have a lot of documents that help you work through this, including the white paper, which is about the suitability of your application and guiding you to the right model. And of course, the folks at Intel are happy to have conversations with you about that and help you find the right place to start. So let me switch over now to the operating environment view. We see this as two computers that happen to be connected by a PCI bus. There's a multi-core computer on the left here, Intel Xeon processor. There's a mini-core computer on the right, which is Xeon Phi. There's a PCI Express bus connecting them, but effectively it's a network. So what we decided to do is formalize that concept. So we actually run Linux. It's a full distro on the left, or whatever you want to put on your Linux system, on your Xeon system. On the mic, we provide an Intel distribution, which is based on LSB, Linux standards based. So all the things you're familiar with POSIX, pthreads, all the standard utilities are there. The ability to log in through SSH, the ability to mount file systems somewhere else on the network, including on the host via NFS. Those are all there. And the idea here is to make a very productive, familiar environment for you. We went a step farther by abstracting the network, or abstracting the PCI into a network. So we've introduced a layer called SCIF. It's available to you if you want to use it. We don't recommend it unless you need it. It's not an industry standard. But SCIF is a symmetric communication interface. And on top of this basic building block of SCIF, which does very low latency, high performance small reads through the PCI bus through what's called the aperture, if you're familiar with that, and memory mapping. And then the other thing is DMAs of large RDMA message copies across the bus using a DMA engine that exists on the Xeon Phi processor. We're able to provide a very simple communication library, which is then the building block for higher level libraries that you're already familiar with. So on top of that, we build sockets, standard Berkeley sockets, so you have an application, you want to try some of these models out, you open up a socket, maybe even just to bootstrap things. Your MPI daemon uses sockets just to build the MP, what are those called again? Now it's called Hydra, but before it was called MPD, I think. In any case, the rings like in the Aragon thing, those use sockets, and if we didn't have sockets, then we could port MPI and get to work in your application. So we made sockets available. We also made open fabrics. So InfiniBand-style RDMA interfaces are sitting there available for you. So if you have code that works on InfiniBand, you should be able to port it directly to Xeon Phi and see what it does. From the programmer's perspective, once you're in the machine, if you take one of these native models and you log in on the right, then all the things that you're used to seeing are there. Math kernel libraries, OpenMP, pthreads, Silk+, MPI, it's all available. If you're on the left, obviously you haven't lost anything. We've gone a step further with some specific offload extensions. So MPI knows how to bootstrap and talk to MPI processes on both sides. So that's symmetric model. We have something called AOMKL, automatic offload. That's where you make a call on the host side. It recognizes that the math problem you've given it is large enough to make use of the mini-core Xeon Phi. Automatically ships the data over, does the calculation, and brings it back. And then, of course, the emerging OpenCL standard is supported as well. Our Linux version is out. for you to test it now. And finally, we introduced some language extensions to make offloading simple from within C++, C, and Fortran code. And we fed that language and those learnings into the OpenMP process because we'd like to see one industry standard come out. I'm pleased to announce that the folks who worked on OpenACC are also participating and fed their stuff in. So the industry is working together to give you one solution, not three, which I think is, again, important for your productivity. So back to this picture, I want to take you through each of these real quickly now and show you what it looks like from a systems perspective. So first, let's look at this offload model. Almost everyone has MPI codes, right? And so the natural thing to do is take an MPI code that exists today, leave it on Xeons, and see how you can make the highly parallel phases that live between messages faster. So we call that MPI plus offload. And in this picture, which was drawn by an engineer, me, which is ugly, there's a network on the left. The Xeons are connected by the network. The data is honed on Xeon processors. Those cells get communicated through standard MPI communication, but somehow in the middle of the calculation, you offload, take advantage of the highly parallel processor, and bring it back. It's fairly straightforward. All the things that you are used to doing are still working. The programmer's thinking of this as a homogeneous network of heterogeneous machines, and the heterogeneity is exploited through offload. The parallelism on the many core is through standard methods. Whatever you would have used on Xeon side, just taken forward and, to a greater scale, a more extreme scale on the Xeon Phi side. Okay. And I don't have time for this, but I put it in for reference. These are some of the simple pragmas that we have to allow you to do that, to effect that offload. And the compiler then generates the code to move the data, execute the function, bring the results back for you. It has a lot. We have whole classes on this and materials that you can download to understand this. But again, this is all feeding into the OpenMP standardization effort. Okay. Returning, remember this picture? I want to look now at the Mike native model, or the many core centric. That was the far right on our spectrum of programming models. There, it's almost like the Xeons are just there to provide power and generate some heat for you and consume some space. So this is kind of a forward-looking thing, saying, okay, if I have codes that are highly parallel and I can run over on here and I don't need the Xeons, I can get a better result, then I would probably be well served by a highly parallel computer in the future, not an add-in card, but a computer. Okay. So in this case, it's really viewed as a homogeneous network of homogeneous nodes. So homogeneous nodes happen to be highly parallel ones versus Xeon ones. And again, the story is the same. Now you do your MPI message passing directly between the Xeon Phis. I'll tell you about how we're making that efficient. But the MPI, logically from the programmer perspective, is just going directly between the Xeon Phis, and the data is honed there. And again, the parallelism inside is a combination of MPI, p-threads, whatever you would normally use for parallelism. Okay. Actually, I want to pause a moment because since this is not a deep technical talk, I don't get a chance to go into this. Intel has some technology that we've developed to support this model efficiently. It's fairly easy to do MPI message passing between highly parallel cards. The question is, I've put all my data on the wrong side of the bus. My high-performance network is over here. It's switches that are connected to host-channel adapters, presumably the FitBand living in the Xeon. Meanwhile, I'm trying to send messages, right? So you can see some of the approaches that have been taken. NVIDIA with their GPU Direct they said, we've got extra copies inside system memory. We've also got extra copies from the card into system memory, out, back into system memory, and then back to the card. And so with the GPU Direct technologies, they're trying to remove as many of those copies as possible. And they haven't been able to eliminate them all. One of the things that Intel's done that I think is pretty innovative is created a system where the InfiniBand card can both write to and read from the Xeon Phi memory directly. So when you do message passing MPI between two Xeon Phis in this way, the data never moves through host memory with a direct transfer. There are some mechanisms we provide for certain types of messages that will actually accelerate it by pipelining the system memory, but you don't have to go through the system memory. We have a direct path. And that actually makes these models feasible, and that's why you were able to see results like that WRF result. In the absence of that technology, you most likely would not have achieved that scaling when you went beyond a single node out to the cluster. So the last model I want to talk about is the symmetric model. And at this point, it should be fairly obvious. Every node looks equal. I happen to show a very regular communication pattern with my MPI, but that was just to keep the diagram simple. This is a fully general heterogeneous network of homogeneous nodes. Everything is independently addressable. All the ranks of MPI have unique numbers. This is a single MPI COM world for communication. And you just type MPI run. You have to discover the nodes and so on and do appropriate mapping of work as I described before. But the basic capabilities to treat this as a homogeneous network, a heterogeneous network of homogeneous nodes is there for you. And several people are starting to explore this model and get some good results. Okay. So I want to wrap up here. I just want to note that Intel's just getting into this game with our first Intel Xeon Phi Coprocessor out in the market, one codenamed Knight's Corner. It was launched at the end of last year. It's now generally available. You can call up your favorite systems vendor and order one with the system. But we've had tremendous support from the ecosystem. Nobody can do it alone. And I want to call out Adaptive's contribution. They were very aggressive about getting Moab support in early. So this community who uses Moab actually is having some of the best and earliest access to this technology. And as I talked about the richness of the different programming models and also operational models, you can see why it's important to simplify that as much as possible for your users, for them to say, I'm thinking this way, how do I get access to those resources? And Moab makes that possible. Okay. The other thing I'd like to point out is that Intel has a lot of resources to help you out if you're interested in learning about this. So I want to point out some of the Intel people who are here. Brock Taylor, do you mind standing? Manages our cluster validation, integration, and enabling team. Anything has to do with clusters goes through Brock. He's going to be here. Find him. Brian Ray, specialist in mic technical marketing, works with companies like Adaptive, software vendors for applications. He's going to be around. We do have a suite at the end of the room. Come find us if you have any questions. I also want to point you to this website, Mike Developer. This is kind of our clearinghouse for all kinds of information, technical and non-technical, on this product line. So anything that I talked about, it goes 10 times deeper here. I invite you to visit it. If you can't find what you're looking for, send one of us an email, and we'll help you find it. Okay. So just to wrap up, this is all about parallelism. It's not about new architectures. If you have highly parallel code, you're ahead of the curve. Take advantage of Phi. If you don't have highly parallel code, now's the time to get it so you can take advantage of these architectures. But the good news is you don't have to change the way you program. You just have to change your program. And as you go, you will see your Xeon performance rising. You will get return. And there will be some natural point that makes sense for you to jump over onto the Phi architecture. So we hope we're doing the right things to take you into this next phase of parallel computing in the most productive way possible. So with that, I'd like to say thank you, and we'll take some questions.